In this video I want to introduce by example arrays in ABC, and as a motivation and application I want to show you how arrays can be used to implement something called a stack. Now a stack is an abstract data type which can be implemented in different ways based on different data structures. In this video we will be very concrete. Our stack offers two operations, a push operation for putting something on top of the stack and a pop operation for removing the last element that was added to the stack. And we will be even more concrete. Elements will always be integer values in our case here. That means, for example, I could perform on an empty stack, a stack which has no elements so far, for example the value 42. Then think of it in an abstract but still kind of concrete way, that I now have a box with the value 42. This is now the one and only element on the stack. If I would push 13, I would have another box on top of this previous box with the value 13. So this would be the state after the second push. Then let's say I push another element 11. Then I have a third box on top of this box with value 13. So this would be the state after three push operations. If I now perform a pop operation, then I remove the last added value. That would be the 13. And then the new element on top of the stack would be 13. If I would perform another pop operation, the stack would just contain the value 42. And if I would perform another pop operation, the stack would be empty again. So this in short describes how in the end you can use our stack implementation. Let's begin with an example for an array. You see I have here a global variable a which has some array type. Now a variable is stored in memory. That means a memory location, a block of memory cells, is used for storing the value of a, which I describe here in this picture. Now what makes a special is that it's an array of integers actually, as the declaration suggests. Think of it as follows. You can divide this box A into 5 boxes, maybe like that, such that each box has the same size. In each box you can store an integer. And you can refer to these boxes with an index. The name of the first box is A bracket 0. The name of the second box A1. And the name of the third box A bracket 2 and so on. And because we started with index 0, the index of the last box would be A4. If we have, like here, 5 integers in total. Now let me draw this a little bit nicer, like that. And here it's important that in both cases, here and here, I'm referring to the same memory locations, to the same memory cells. Sometimes, like here, I want to point out that this memory cells, this block of memory cells belongs to variable A. And in the second case, I want to point out that this block has this structure, that it consists of 5 integers which come in memory one after each other, without a gap in between. And in function main you see that I can assign to this elements of A values. For example, after this first assignment here, this box here would have the value 123. And after the second assignment we would have in this box the value 42, and so on. Also try out the following. Assign a value to an array element which is not existing, for example to A5. Let's say the value 12. Now a mistake like that easily happens because you just look at the declaration, you see you have an array with 5 integers. You forgot that counting starts with 0, so you might think that the last array element has the name A5. Then you do not get an error message from the compiler. The compiler simply generates code which assigns to this memory block that the value 12 when you run the program. And what happens then is undefined behavior. Maybe this memory block is used for another variable, then you by accident overwrite another variable, not an array element of A, but a completely different separate variable, or the program might crash or it might not crash, or some days it's crashing, another day it's not crashing. The typical thing, the typical problem with undefined behavior. Now the reason why the compiler is not complaining about that is that ABC inherited this from C, this philosophy, trust the programmer. So the compiler simply assumes that you do the bookkeeping for arrays correctly, that you only use an index which is valid. You also can try the following, that you assign a value to A minus 1. Let's say 34. Then the compiler is also not complaining. It simply generates code which will assign the value to this block of memory. And then again, you have undefined behavior when you run the program. So the program might crash, it might show some strange behavior, or in the worst case, everything seems to be fine most of the time, but then one day everything goes south. Of course, instead of defining an array with 5 integers, you also simply could define 5 integer variables, which you could denote A0, A1, A2, and so on, up to A4. This would have the advantage that the compiler actually would complain if you then access A5, because if you only define these variables, you would get an error that A5 is not declared. The advantage of using actually an array is that you can use a variable, like for example here variable I, for accessing a certain array element, like here in a loop. And this is the reason why you usually use an array. Here you have the responsibility to make sure that you know what is the largest value of I in this case. And here a typical error would be to have a condition I smaller equal 5. Then you actually would access A5 in the last iteration. And then you again would have undefined behavior. Now keep in mind that when you work with arrays, you as a programmer have to make sure that the index is always valid. Like in this example, you have to make sure that the index is in the range from 0 to 4. Now this is annoying that you have this much responsibility, but that's in certain cases the price that you have to pay for no runtime overhead, more efficiency. What you don't want to have is that the compiler, each time you access an array element, is first checking whether the index is valid and only then accesses this element. Now in some cases the compiler actually could help you more. It could detect at compile time, when it's generating code, whether an index is correct or not. A case for that would be if you, for example, would have this statement, A5 gets overwritten with 12. Then the index 5 is known to the compiler at compile time, and the compiler knows that array A only has 5 elements, so 5 is not valid, and it actually could and actually should at least raise a warning. A case like this here is a bit harder. Here the index is the value of a variable, and in general the compiler first has to look into the variable, then analyze whether it's valid or not. So it basically would have to generate code like that, where you have an if statement, and in this if statement you first check whether I is non-negative and not larger than 5, smaller than 5, and only then accesses this array element, and otherwise generates an error, a runtime error. And if you would have something like that hidden behind an access to an array element, then you would have some runtime overhead. Now actually this is still a bad example, because a compiler could look at this part here And from here it's obvious that I only can have the value 0, 1, 2, 3, 4. So it could statically analyze what values of I are possible and therefore could check that this is always correct. But let's assume the example would be changed so that 5 is no longer a literal, not known at compile time, but some variable n, and the value of n comes from some user input. Then it would be impossible for the compiler to check at compile time whether I can have invalid values for an array index or not. And then you only can get help from the compiler if the compiler adds some additional code which gets executed at runtime, which is checking whether this index is in bounds. And this is something that you don't want to have, at least not in the philosophy of C or C++, where you do not have any implicit runtime overhead. If you want to check whether index is correct at runtime, you have to add this if statement by yourself. Now for implementing this error checks, this bound checks, you actually can get some help from the compiler, because internally the compiler is keeping track about the sizes used for variables. For example, the number of bytes for an array, the number of bytes that are used for an integer. And with the size of operator, you can access this information. For example, you see on my machine, size of A gives 20, and that means 20 bytes are used for this array. So it's basically the width of this memory location. So let's write this down. This is the number of bytes for array A. And size of A0 is the number of bytes for A0. So the width of such a box. And down here, I'm dividing the size of the array by the size of a single element. So this gives me the number of elements in A. Now on my machine, size of A is 20. The size of A0 is 4. Here, by the way, I also could use A1, A2, A3, A4, because every element of the array has the same size. But A0 is a sure thing, because an array always has at least one element. So it always works with A0. That means down here I basically have 20 divided by 4, which is 5. Now one important thing is that size of is not a function call. Let's write this down. Why is this important? Because a function call would mean that something gets done at runtime. But size of A gets replaced with 20 at compile time, because the compiler knows the size of its variables. And it also replaces size of A0 with 4 at compile time. That means the compiler also sees here that 20 should be divided by 4, and this computation also does not get executed at runtime. The compiler simply replaces 20 divided by 4 with 5. That means with an expression like here, you have a nice and robust way to denote the number of elements in an array. It gets replaced by the compiler with 5. This means if you change this here to an array with 7 elements, you get here immediately 7, because then the size of the array would be 28, and that means you would have here 28 divided by 4, which gives you 7. After this quick introduction of arrays, I now can show you a simple implementation of a stack on which you can store up to 5 integers. And for the implementation, I use an array for storing the elements, array stack with 5 integers, And I also have here this variable stack size, which is initially 0. So let's also denote this here in this graphical visualization. Now let's simply follow the control flow of the program. Basically, we debug the execution. We begin with the first statement in function main, which calls function push with argument 42. That means in the first call of push, val is 42, and this gets assigned in this statement to stack with index stack size. Because stack size is 0, that means we write to this element the value 42. After that, the stack size gets incremented. That means after that, we have here a 1, and then we return. That means then we execute the second push call, where we get 12 in parameter val, and that means the 12 gets assigned to stack with index 1, because stack size is now 1. That means here we have afterwards 12, and then we increment the stack size. That means after this function call, the global variable stack size has the value 2. And then we have the third statement, which is actually a print statement where in one argument we have this function call to pop. Now what pop is doing, it's first decrementing the stack size. That means here we now have the value 1, and then it's returning the element of stack with index 1, which is 12. That means here we print 12. And then in the next call to function pop, we repeat this. We first go to function pop. We decrement the stack size, so it's now 0. And then we return stack with index 0. So that's 42. So here we have 42. So very simple. At the beginning of the video, I described the stack with boxes that I can put on top of each other and where I can remove boxes. Let's review this example in this context once more, where I describe the situation with boxes on a table and how this idea is realized in this program. So initially we have an empty stack. That means we have a table without any boxes on top of it. So this is an empty stack. And this describes basically the situation when you start the program and before the execution of this function called push started. So we are in the program right here before the push 42. And in the program, that means that stack size still has the value 0. Then we enter function push, and then two things happen. First, because stack size is 0, it means that this element here, the element stack with index 0, will be used for storing the argument that we passed, the 42. So 42 gets written into here. Then we increment stack size by 1, and that means the next time we would call push, this element gets used for storing the argument. And on the table, we can think of that as there is now one box with the value 42 in it. And that's the situation after push 42. Then we call push again with argument 12. Then we again enter function push. We again first write the value into the variable with index stack size. So basically you can think of stack size as a pointer which points to the array element which should be used next, and into this array element we now write the value 12. And after that we increment stack size, so it's then 2, and that means the next push operation would write something into here. On the table, this means we now have a second box with value 12. And here you can basically see the meaning of this illustration and how it's realized in the program. Basically everything on the left of this arrow, which is basically just a graphical illustration of the value stack size, refers to a box on the table. Now what happens next? Next we perform a pop operation. That means in our understanding we remove a box, this box here. What in the implementation actually happens is the following. We first decrement this value stack size when we entered function pop. So it then will be 1. That means we refer to this element. The value of this element gets returned, and that's it. Now, in our understanding, this box should have been removed. But if you look into the memory, the value 12 is still there. But still, when you look at this arrow, the meaning of this arrow is that everything left of it is a box which is still on the table, and everything right on it is basically invalid or can be used for a push operation. Then let's go back to the execution of the program. We perform another pop operation. We again enter function pop, decrement stack size, so that would be now 0. That means we now refer to this element, return its value, and that's it. And in our understanding, everything left of it is what we still have on the table, which is in this case nothing. The stack is now empty. So this is important, that removing elements in our implementation doesn't mean that we write some 0 into the memory. I mean, that wouldn't make sense because we also might want to store a 0. So having a value 0 in here doesn't mean that the box does not exist. Whether a box is existing or not simply depends on the value of stack size. Everything with an index smaller to stack size refers to a box that does exist, and everything greater or equal to stack size refers to a box which is not existing. Of course, the implementation of our stack actually could use some error handling, because if you would call push here more than 5 times, we would have a stack overflow. We only have memory for 5 elements, and calling push 6 times without calling in between some pop simply would mean that we have some undefined behavior. Also, if we would, in this example, call here pop more than 2 times, we would have undefined behavior, because we just have, after these 2 push operations, 2 elements on the stack, and if we would call pop a 3rd time, we would access this element, and that would be undefined behavior. And of course, we should handle these cases, at least with an error message, so that we don't run into this undefined behavior thing. But before I go into that, let's first look at this example where I made a modification here and here. And here I basically want to talk about the 2 variants of this increment and decrement operators. Here I'm using the ++ operator, but you see the ++ comes after the variable. And this is the so-called postfix ++ operator. Here I'm using the -- operator for decrementing the variable, and you see this - comes in front of the variable. This is the so-called prefix - operator. Now both the ++ operator and the - operator have these 2 variants. You can use them as postfix or as prefix operator. And what they have in common and what the difference is, I want to show on the next slide. You see I'm using here the prefix ++ operator, and the meaning of this statement therefore can be described as follows. We first increment the value of a by 1. We also could write this as a equals a plus 1 or as a plus equal 1. but let's keep it simple. So we first increment a, and afterwards we assign the value of a to b. So b gets overwritten with a. And here I'm using the postfix ++ operator. And here the meaning of this statement can be described as: we first assign to b the current value of a, and afterwards we increment a. And that means here we will see that a has the value 2 and also b. And here we see that a has the value 3 because a was incremented at the end, but b still has the value 2 because we assigned to b the current value of a. And this concept we used here. We first take the current value of size t for referring to the element to which we want to write val, and after this was carried out, the value of stack size gets incremented. Whereas here, we first decrement stack size and then we access the element of stack with the now updated value of stack size as index. For error handling, I'm using assertions. You see here assert and here assert. And the meaning of this assert is very simple. You have assert, and here you have a certain condition, which can be true or false. If this condition is true, then nothing happens. If it's false, the program crashes with an error message. And this at least gives you always defined behavior. You cannot, and that's the purpose of this, you cannot push something on a stack if it's already full, because I'm checking here how many elements are already on the stack, and this number has to be smaller than the number of elements that actually can be stored in this array. So this is the pattern from before for determining the number of elements in this array. For the pop operation, I simply check whether at least one element is in the stack, and only then we basically return the element. Otherwise, the program will crash here. So that's it. And of course, in the exercise, we will do more examples about that. But here you have the fundamentals.